All right, so welcome back to this last in the series of lectures on spatial statistics and spatial econometrics. Uh, we are going to today look at the Lagrange multiplier test for spatial dependence in regression models. It's a short lecture on hypothesis testing in spatial regression models. This is just an introduction. The idea of this lecture will be to ramp you up in order to learn about hypothesis testing in regression models, or rather spatial regression models, but in no way this lecture is going to be exhaustive in doing that. Okay, so but having gone through this lecture will then sort of enable you to study these concepts elsewhere in detail. Okay, so of course, we are going to look at the two models that we have seen in detail, that is the spatial lag model and the spatial error model. And if you remember, the spatial lag model looked like this. So we had y equals rho wy plus u, and the spatial error model was y equals, sorry, I missed something here. So in this spatial error model, I had this x beta, right, plus u, and in the spatial error model, I'll have y equals x beta plus u, such that u is equal to lambda wu plus e, where e is multivariate normal with zero mean and a homoscedastic variance covariance structure. Right, so we've seen these things in detail by now. Now, we can just revise this very quickly. So let's look at the spatial lag model. So we have y is a n by 1 vector, which is just data of delineated by space or locations. W is a weights matrix, a very precise or let's say a concise container for spatial relationships between the units of analyses, right? So W is an n by n matrix, Y is again n by 1. So all I'm looking at is an n by 1 matrix. We have defined this as YL, which is the spatial lag notion of modeling spatial processes, just parallel to the time lag, right? X is an n by k matrix of k covariates, and beta is a k by 1 vector of coefficients. U again is an n by 1 random term, error term, comprises of everything that we could not model, in this quest for measuring or explaining the variation in y. The spatial error model is slightly different. Instead of including the spatial effects in the mean outcome model, it includes such effects in the error process. And in the last or couple of lectures ago, we saw that such models make sense when you have a spatial mismatch between the underlying population process and the data generating process. So if you are studying land use change, but which is a more high resolution process happening at farm levels, and but what we are doing, but when we get data, if those data are at district level, then we are going to have a error term misspecification, in the sense that we are fundamentally misspecifying or misrepresenting the population process, and that enters the random error term, right, which we can then specify as a spatial error model. What is the aim for hypothesis testing? Hypothesis testing wants to figure out whether it makes any sense to include these spatial effects in the models, or can we just live with the non-spatial models that we are very used to, even before we studied this particular course, right? And that will depend on whether or not rho is equal to, if rho equals 0, then I'm done. I don't really need to worry about all the weights matrix and all the computation and all the techniques that I need to sort of imbibe for conducting spatial regressions. But if rho is not equal to 0, then I can't run away from this situation. Similarly here, if lambda is equal to 0, I can go back and to my traditional analysis, something that I know of regressions before even I studied spatial regressions or spatial statistics, right? And if it's non-zero, then everything that we have studied in this course kicks into action. and that will lend us our null hypothesis and our alternate hypothesis for this particular exercise. And the test that we are going to use is going to be a Lagrange multiplier test. So let's dive right into it and figure out what is the aim of doing all this and what are the statistics that we are going to use, right? So I'm going to start with the spatial error model. Okay, so I have y equals x beta plus u such that u equals lambda w u plus e, where e is multivariate standard normal. Okay, not standard normal, multivariate normal with mean 0 and variance sigma squared, and variance covariances, the covariances between the E errors are 0, right? Of course, now my null hypothesis is that lambda equals 0, and my alternate hypothesis is that lambda is not equal to 0. If I reject my null hypothesis, then I can just say, I can work with traditional tools. I don't need all these spatial regressions, right? So the test statistic, the Lagrange multiplier test statistic, LME, is given as u prime wu divided by s squared. S squared is just, a sample variance, right? So s squared, the whole squared divided by t, right? This is distributed chi-squared with degrees of freedom, 1 degree of freedom. Okay, it's distributed chi-squared with 1 degree of freedom. Okay, now s squared is nothing but u prime u by n, and t is a trace of w plus w prime dot product with w. So now let's look at what are we really writing here, right? It's a lot of notation. Now, what's up with the Lagrange multiplier statistics? So this numerator, this u prime is 1 by n, this is n by n, w is n by n, and this is n by 1. So I am looking at a scalar 1 by 1. The scalar 1 by 1 is divided by s squared. S squared is nothing but u prime u. So again 1 by n, n by 1, I have a scalar sitting here. This u prime u can also be seen as summation I ui squared. So it's the sum of squared errors divided by n, which is nothing but the sample variance. But this sample variance, s squared, is as if there is no spatial weights. Okay, so the numerator here is looking at the sample variance modification when we have spatial weights versus when we do not have spatial weights. This numerator is then, a square of it is then normalized by this factor t. You can think of it as a normalizing coefficient, and this is a function of the weights matrix. So now I have a weights matrix n by n, its transpose is n by n. You multiply it by n, I have a square matrix of n by n. The trace of a square matrix is just the sum of its diagonal elements. Okay, so whatever matrix that I get here, I will sum all the diagonal elements and I will then normalize. So I have a, the trace by itself is a scalar because it's the sum of all diagonal elements. So I have a scalar sitting in the denominator, I have all scalars here. And because ultimately here I am comparing the variation or the variance in presence of weights and in absence of weights, the appropriate test statistic is a chi-squared statistic. If you have studied statistical inference before, you will know that even if you are comparing the variances of two different samples, you use a chi-squared statistic. Okay, so the Lagrange multiplier statistic is a very natural statistic to study or test the hypothesis that whether lambda is equal to 0 or not equal to 0. Okay, so of course what I need is a test decision. What is a test decision? Well, if LME is greater than chi squared 1.95, so we say we reject the null hypothesis at 95% confidence. And if LME is less than or equal to chi squared 1.95, then you say you fail to reject null hypothesis at 95% C. So if you fail to reject the null hypothesis, then you may not want to specify a spatial error model. But if you reject it, then the spatial error model is indeed the right specification. If you ignore it, then you are going to have inefficient estimates. Okay, you are going to have larger errors in your beta hats than you would have ideally wanted. Okay, so if you reject the null, right, that means lambda is indeed going to be less than not equal to 0 and is likely to be not equal to 0 with a very high probability, and so probably you should apply a feasible generalized least squared model. But if you fail to reject the null hypothesis, then you can live with OLS. You're fine. So that's what this null test hypothesis testing exercise is telling me. Okay, so I'm going to do a similar thing for spatial lag models. Let me do that for spatial lag model. We'll quickly write it down. Y equals rho WY plus X beta plus U, and now my null hypothesis is either rho is equal to 0, rho is not equal to 0, much more natural. Just like earlier, I'm going to define a test statistic. This time I'm going to call it LML, that is the lag. This is going to be U prime WU. Oh, not U this time, it's going to be U prime WY, because now I'm explaining the variation in the mean outcome and not in the error outcome. This divided by again S squared whole square divided by a normalizing constant Nj. This is again going to be chi squared 1, that is chi squared distributed with 1 degree of freedom, right? And S squared, just like earlier, is just U prime U over N, right? And Nj is equal to T plus Wx beta prime M Wx beta divided by S squared, where T is equal to the trace of the same matrix that we are used to by now, right? And M is a projection matrix, I minus X prime X inverse X prime. Sorry, I have, there's a typo here, I needed, okay, I'm going to rewrite this. M equals I minus X prime X inverse X prime, and then close the bracket. Okay, this is a projection matrix. The idea is the same. Now the expression is a bit more complicated, but the idea is exactly the same that we have seen earlier. Okay, and of course what we are interested in is the test decision. That is, if LML is greater than chi squared 1 at 0.95, this can be sourced from a chi squared table, then we will reject the null at 95% confidence. Okay, and if LML is less than or equal to a chi squared 1 at 0.95, which again will be sourced from the table, we will fail to reject the null at a high confidence of 95%. Okay. Now, if you reject the null, then you cannot avoid a spatial lag model. That is indeed the right specification. And if you reject the null and you still go on to ignoring, if you go on to ignoring this rho WY factor, then all the beta hats are going to be biased. And higher the rho, the greater is the degree of bias, something that we saw through a simulated plot by Luca and Celine earlier, right? And if you fail to reject the null, then you can go back to your OLS, just like we talked about in the previous case. Okay, so ultimately we are also often interested in choosing between these most appropriate specifications. So this is the starting point, right? If I am interested in choosing between whether I should run a spatial error model or a spatial lag model, then the starting point is to first figure out whether individually they make sense. If say both individually make sense, then probably we should go back and look at a likelihood ratio test, something that I'm not going to talk about here. But basically what you're saying is I'm trying to maximize likelihood in estimating the spatial lag, in estimating the spatial error. I want to see which fits my data better. Okay, so we have to apply, again, as I said, this module on hypothesis testing is a very basic introduction. It does not do justice to hypothesis testing in spatial regression models at all. But it's a ramping up exercise. I'm trying to empower you in order to now go back and read the book and figure out how to conduct hypothesis testing in various different settings of with spatial regression models. Okay, so with that, I'm going to end the lecture modules of spatial statistics and spatial econometrics. Going forward, we are going to move to tutorials, that is hands-on exercises with ArcGIS and R, right? So I want to congratulate you for making this far, and the rest of this course is all software driven, and it is basically working with actual data and applying all these theories that we've been learning over the course of last almost 10 weeks now. Okay, so thank you very much for your attention, and I'll see you on the other end with the hands-on exercises. Thank you.